Okay, so
Perfect.
over to you, Lara. Please, we're ready to go now.
Perfect. Thanks. No. Okay, you see my screen, right?
Yes,
Perfect.
I see
Okay.
your
Hi.
screen and also your pointer.
Yes. So hi everyone. Nice to see new faces. As the column said, I'm a new research fellow at ICCS in Cambridge, and decided to discuss this paper because, as yes, it was kind of, well, let's say inspirational in the sense I worked with Sarah Perkey over the last few years. Like before moving to Cambridge, I was a postdoc at Scripps Institution of Oceanography, where I work with Sarah, and so this is one, it's not the most, let's say, recent paper, it's from 2010, but it kind of set the research questions that we kept trying to address also with my postdocs, and basically try to address some of the issues raised in this paper. The big picture is that it really focuses on the role that the ocean has been playing in taking up heat. And so the contribution really of abyssal waters to global heat and sea level rise budgets. What is reported here is actually the first sentence of the paper, and this was just mostly because, I just found the change in language, I guess, over the past decades interesting, in the sense that apart from stating that warming climate is unequivocal, in this sentence in 2010, we're stating that this is very likely due to anthropogenic greenhouse gases. And this was still, I guess, following the former IPCC report. And this is more just I was just nicely surprised to see that in the last decade, also the causality of the changes, the language linked, with the causality of the changes has changed. And so in the last IPCC report, IR6, which came out in between 1 or 2 years ago, also, again, the fact that this is unequivocally caused by human activities is stated, which was, I guess this is more a connection with climate policy and how important it is actually to have that in these reports. But yeah, so we know again that the climate has been warming, but we also know that the ocean has already been playing a very important role in climate mitigation, and by taking up to 90% of excess heat, which is what is shown in the panel here. So this shows the contribution of the different components of the climate system to the global energy inventory as a function of time. And so it shows basically, again, that the largest contribution of the ocean in taking up this excess energy, and about half of this 90% has been taken up in the top 700 meters, and the remaining has been taken up by the deeper parts of the ocean, which is really then the focus of this paper. And then just to, just a sec. Okay, this is just, sorry, it's a lot of text taken from the paper, but it's basically just to point out that kind of also why we care of how much basically heat is taken up is also because, of course, it contributes to sea level rise in 2 ways. One is through just thermal expansion, and the other is through increased melting of continental ice. And also the fact that all of the basically budgets in heat and sea level rise are, one of the big limitations is really actually how the fact that they rely on poorly constrained budgets for the deep ocean. So this is really where we have the estimates here are observationally very poorly constrained, and also the models are, when it comes to basic representation of a deep ocean, we know that they have all sorts of issues, from different lower resolutions to longer time that it takes to equilibrate the circulation there, and to the fact that when we end up with models that represents the propagation of signals, including the heat, for example, from the upper ocean to the deep ocean in different ways. And so how they represent this exchange of heat is different and leads to large uncertainties in climate predictions, which was then, if you want, the motivation of this paper, trying to basically more have try to observationally basically constrain the contribution of abyssal waters to, again, global heat and sea level rise budgets. Before digging into the paper, since honestly I wasn't sure about the different backgrounds of the audience here, this is really very quick 2 minutes intro if you want, at the circulation that we're looking at. which is very briefly described in the paper. The main point is that like this mitigation role that the ocean has been playing has again taken up 90% of excess heat, but also about a third of anthropogenic carbon, is strongly regulated by the global meridional overturning circulation, which is what is shown in this schematic here. So it's formed by different interconnected overturning cells that span all ocean basins. The schematic also like highlights the crucial role of the South Ocean in actually linking these different basins. And this is, I guess, also, I mean, it's partially also why this paper focuses on the waters originating here. In this schematic, like the red lines and arrows, associated arrows show the surface flow, while like the blue and the purple arrows show deep and abyssal flow. And again, the deep ocean, which again is the focus here, is mostly ventilated by water masses formed either in the North Atlantic, so the North Atlantic deep waters, or around Antarctica, forming the Antarctic bottom waters, which are formed like in different locations around Antarctica, and then they contribute really to like the densest water masses here, and it's basically represented by, if you want, the purple arrows in this schematic. And to give you an example, actually a very quick example of how this circulation contributes to like the uptake and distribution of different properties. This is actually anthropogenic carbon, but the point will be similar for the anthropogenic heat. Like the colors that appeared here show the depth integrated anthropogenic carbon from GLODAP, which is like a data set basically compiling different hydrographic data all together. And some patterns emerge which are clearly linked with the underlying circulation. Actually, the Atlantic Ocean is a crucial example because it shows that the high concentration in the Atlantic Ocean are linked, be caused by the formation of dense waters in this region. And this is also why the high concentration are largest in the western side of the basin. And similar like in the South Atlantic, again, high concentration associated, especially close to the western boundary, because again of the presence of, in this case, abyssal waters. But there are signals that especially the regions also where dense waters are formed have been changing quite rapidly over time. And so this paper was really trying to understand basically the changes happening in the South Ocean. And so going back to the paper, as I said, like it really wants to focus on the contribution of Antarctic bottom waters. So what I mean, this is a figures that actually, I mean, there are different parts of these figures that are linked with the paper. The first is like, what data do they use? They use the data from like repeated ship-based hydrographic sections, which are the black line represented in these two plots. So these observations started in the 80s and are continuing now. They started with like the world ocean, what was called the world ocean circulation experiments, and are now maintained by GoShip. It's an international effort, is the Global Ocean Ship-Based Investigation Program. And we mostly, in this, specifically in this paper, we use then all the CTD, the temperature observations, basically, that have been collected along all of these sections. The colors in this plot shows the fraction of Antarctic bottom water. In the top panel, it's a fraction of Antarctic bottom water below 4,000 meters, which is like a very limit that is used in this paper. They set a depth limit mostly because they want a fixed volume to then later calculate the heat and sea level rise budgets. And so below 4,000 meters, most of the Indian and Pacific especially are filled out with Antarctic bottom water. In the Atlantic Ocean, the story is a bit different because we know we have endemic formations of dense waters in the North Atlantic, and so we can basically see a clear signal of, I mean, the largest fraction of Antarctic bottom water here, it's in the South Atlantic as expected, and is decreased further north. But still, overall, like looking at the global picture, basically, all the, again, results discussed here are linked mostly with like waters that have that are within or that have originated within the Southern Ocean. And then they also look at like the budgets basically within like different regions. So it's not focusing only below 4,000 meters, but it's looking at the area between 1 kilometer and 4 kilometers south of the subantarctic front, which is the pink line shown here. And this is basically where the density surface and outcrop and come in contact with the surface like in the Southern Ocean. And so again, this part is basically where we have like a large contribution of Antarctic bottom waters. So what I mean, but there is a big section on data, which I'm not going through, in the sense like, you know, describing all, if you want, the details of how they selected the data, which cruises have selected, when these have been sampled, and they take, of course, into account like the fact that some sections might be biased because highly sampled in some decades and not in other decades, and so on. So this is I'm skipping through that, but there is a lot of like, you know, details in that eventually could affect a bit the results, but they are quite carefully taken into account. So just jumping like to the actual analysis that they ran throughout all of the sections basically that were shown in the previous plot. The first thing is to look at temperature changes at each location. So we actually interpolate each cast on a uniform density, uniform pressure levels. And then at each level and each location, basically look at the changes in temperatures over time. When 2 or more occupations are available, they use like a linear fit. And so the change in d theta dt is represented then as like the slope of this linear fit. Which they do mention generally, like sections with 3 or more occupations show a monotonic like trend. They also mention that they calculate also the errors of this fit. So basically looking at the variance of the misfit between like the predicted the predicted basically temperature by the linear fit and the actual observations, but they kind of don't discuss that a little later on. So they don't really talk about how much a linear fit is actually good in general. They kind of drop the conversation a bit, but I'm actually, we are basically updating these estimates with Sarah again. I have a plot later on, and we're now going back actually to look at that, basically the accuracy of the linear fit, which in general is not necessarily always a good model, as you can imagine. And then, so the plot here shows like an example of that like temperature change analysis done locally. And the section here, this is one of the sections in the Pacific, shows their results as like a like pressure latitude section. So we have again like a local, if you want, like changes in the either basically showing like a warming or a cooling rates. They discuss about like just a little bit about how these are like then combined into the different basins, which actually I have not really discussed. But just skipping back to this figure, all of these gray thick lines shows like how they separated the different basins. And this is mostly due, I mean, the criteria are topography, so the presence of ridges, which is like the main criteria, and then also looking at the temperature in abyssal waters across like these different basins. And so every time basically with a comment on like, you know, an analysis basically done within a basin is like again in each of like basically these portions of the oceans. and which will become clearer, I guess, in a second, because that's also where we calculate the first way we calculate like the local like heat and sea level rise like budgets. One thing about, you know, the temperature range analysis, they comment on the fact that using different time intervals doesn't really in general change the results. This is in the sense that taking, for example, the differences between like two occupations, like the first and the second occupation, or the second and the third, or like the total change overall gives like similar responses. So they always like look at like the changes again over like the largest time period, but assuming that again, it's a good representation. And okay, and this is like, if you want, like the key figure of the paper. And so from the temperature change analysis, they calculate the flux at 4,000 meters, basically by like integrating then the temperature changes like between like the bottom and 4,000 meters, and then dividing by the area per each basin, which is what is shown in the top panel here. And similarly, then they repeat the analysis, changing like so rather than having basically heat capacity, they have the thermal expansion coefficient to calculate then the sea level rise. So the contribution basically of that, the inferred heat flux to thermal expansion, and so to sea level rise. And the key point here is that there is quite a clear global pattern that emerges, and that that global pattern really follows the pathways of Antarctic bottom waters. And so first of all, the main thing actually, which is not shown here, but I will mention for a few. So they don't show in this figure which well, I mean, it's quite easy to see it from the numbers, but which basins basically have statistically significant trends. But all of the ones like close to the formation regions of abyssal waters have significant trends. And then the level of significance usually decreases as we move away basically from the formation regions of Antarctic abyssal water, Antarctic bottom waters. And so, I mean, again, the pathways, I'll just guide you through some of this, but it's quite obvious in the sense that we have, I mean, one of the key regions of Antarctic bottom waters is the Weddell Gyre in the Atlantic Ocean here. I hope you can see my cursor. I assume so. And I see Marla nodding. Thank you. And yeah, so we have like, this is again a key region, so information of Antarctic bottom waters. And then from here, they basically, sorry, I managed to go to the next one, but they move forward, northward, following again, mostly the western boundary. And so we see again, the warming basically being affected by these waters in the western South Atlantic. Once like then part of the abyssal waters continues like their pathway northward in the West Atlantic, and part of them cross basically the Romanche fracture here and other fracture zones, and then they move like into the Western Atlantic. But all of this, like I mean, this is actually the only slightly significant, but all of these other like basins, like trends, are usually not significant. So again, the only ones really significant are in like the Brazil basin here and close to the formation regions. And again, when we move to the North Atlantic, especially, and the eastern part, especially of Atlantic, here the contribution of Antarctic bottom waters is much reduced, because we are actually talking mostly about North Atlantic deep waters. So these trends, the fact that they don't really agree in that sense, is not inconsistent with the results. Then in the Indian Ocean, there is quite a clear separation along this ridge here, which, sorry, I forgot the name. I'm terrible with ridge names. But the point is, like, there is warming trends like to the east of this ridge. And these are mostly caused by waters coming actually from the Ross Sea, which is here. It's another, again, key region of Antarctic bottom waters. And so these waters basically, again, move westward and recirculate in these basins. They talk about the basin here, like just south of Africa, as a bit of an anomaly in the warming. But actually, I mean, it's not statistically significant, but I don't think it's in that sense an anomaly, because with actually more recent work looking at other tracers, we saw that there is a very fast actually pathways for waters formed in the Weddell Gyre to basically move eastward and then delete this part of the Indian Ocean. So this is actually could just be again a signal of the waters forming the Weddell Gyre that are moving northward. And they do so, we saw from again other traces, which I will discuss a bit just briefly at the end in like 30, 40 years. And finally, like again, the Pacific shows overall warming. Warming is decreased as you move northward, because again, it's mostly caused by waters originated in the Southern Ocean. And quite interesting, actually, this is still significant, even if I mean, it takes usually, I mean, we'll just actually go back to this later. And I mean, the patterns in terms of like for sea level rise, I mean, I agree, of course, with this, with one of the heat flux, because again, that's basically like the consequence of this heat flux. In terms of the actual numbers, one thing to point out, which is actually the pink values here. So if we were like to look at the heat flux across the whole Southern Ocean, and not like below 4,000 meters, but again, in this case, the criteria is all what they call the deep Southern Ocean, so between 1 and 4 kilometers. The contribution is quite large. It's about 0.9, like with large uncertainty, but about 0.9 water per meter square, and that contributes to about 0.9 millimeters per year of sea level rise, which I'll put like in the general context in a second. So this is from 2010. I don't actually have updates from in terms of like from this specific analysis for the sea level rise, but when it comes for the warming, the plot here shows actually an update of this analysis in 2019. Sorry, I'm just looking. Oh, okay. No worries. Why? And sorry, but I was checking if it was a question. And so this is like, again, it's an update in 2019. It means that it uses also all the repeated sections like from basically between 2010 and 2019. I actually had the version up, well, I couldn't find it. I have a version basically updated to last year, and it's quite similar. It's not very visible here, but all the solid basically basins are the significant ones, and all these stippled ones are insignificant. Overall, the patterns have not really changed a lot, maybe except, I mean, they included a few other basins, which were not included here, basically because there were no observations. And some basins like the Atlantic one has changed, but again, it is still not significantly different, like statistically significant. So again, overall, this is like, it's still like quite similar to basically my most updated ones, also because, I mean, it's not every time that you think about new data, consider there are maybe 2 to 3 cruises that can be done per year, and are not necessarily like crossing that sense of Southern Ocean regions. And then, okay, so, and this is like putting it like into a global estimate. So what was shown before, it was like a local, like around each basin, of course, with the assumptions that the few sections that actually cross the basin are a good representation of the whole basin area. And with the, so the assumption that at each pressure, like the changes observed at one pressure will kind of be again like similar, like at the same pressure, like throughout again the whole area. So it's not necessarily always a good assumption. Some basins specifically have maybe one section really crossing them, so it's very like highly skewed towards like that. I mean, of course, the only values that we have. So that's always something like in that sense to keep in mind. And then basically they look at the global heat and sea level rise budgets by summing like the contribution of all the different basins and dividing by the total like surface of the Earth. So this is in like the area included is in that sense much larger. It's not just like the ocean area, it's just like it's the total area. So it includes lands as well. It includes also all the like, just going back, all the white areas, basically, and all the gray ones. And that is done just to put it more in the climate context, like basically so that we will have basically numbers comparable with like the energy imbalance at the top of the atmosphere. And so really like what to focus is was two things actually started from the figure. This shows like the heat at each depth. Like the first panel is for the global ocean and the second one is only for the deep Southern Ocean. And here the key point is like that, yes, I mean the deep Southern Ocean contributes partially, but including actually the global deep abyssal waters is important in calculating like the global like heat budgets. And this is mostly because, well, we know that the Southern Ocean has been playing a key role, but the point is like looking at what happens below 4,000 meters is in that sense important. And these are on like the same scale, which is what is shown here. Which, well, I mean, I don't know, I somewhat agree with this, but this seems in that sense to me always a bit contradicting, because when if you look at the numbers, like the total like heat budget, like for the global ocean below 4,000 meters is about 0.095 water per meter square. And this would be adding, sorry, the contribution of like everything that happens, like, sorry, this is the 0.027 is what happens below 4,000 meters, and this is adding the contribution of 0.68 of everything that happens in the deep Southern Ocean. So the point is like the deep Southern Ocean is actually a huge contribution to the heat budget and a big contribution to the sea level rise. So to put these numbers, which in the per se, I mean, to put this number in context with what is happening, for example, in the upper ocean, we know that the upper ocean in terms of like the heat flux, like that was reported at least up to 2008, but again, it hasn't really changed in that sense a lot, is 0.64 watt per meter square. So what is happening basically, the total contribution of the deep ocean is about 16% of that, which is in that sense not too large, but at the same time not insignificant to not be included, which is, I guess, one of the main points. And when it comes to sea level rise, the global, again, sea level rise estimated in the upper ocean is about 1.6 millimeter per year. So the contribution in that sense of the deep ocean is overall smaller, much smaller. But one of the key points that they point out here is that this could have also very large, like regional variations. And so I'm trying to get the number because I don't think I reported it here. But yeah, so for example, actually looking at everything that happens, which is here, it is here, but everything that happens like in the deep Southern Ocean is about 1 millimeter like per year. So the point being is that in terms of a net contribution, it's just 9% of what happens in the upper ocean, but locally, like especially like in the just a fraction of the deep Southern Ocean, if you look at the local regional patterns, it is not like very dissimilar to some of the patterns that you could see in the upper ocean. So it's as a so sorry, this I'm kind of confusing myself, but that's, I guess, what the warming in the local contribution from the deep warming in some regions, like south of the subatlantic front, is not especially insignificant. And then the last bit really is about the possible causes of the warming, and we discuss a few. Well, actually, before discussing really the warming, they mentioned that part of the warming is just likely caused by advection of warmer waters, in the sense that waters basically have warmed up and they are being advected around. And that is mostly because we do see that the warming patterns are really consistent with what you know about abyssal circulation. And there is one thing that I mentioned that to kind of justify in the sense that outside the Southern Ocean, the advection is basically, basically the advection times in the Southern Ocean are much longer than the observations used here, which is in general true because the mean age of, for example, the North Pacific, of the deep North Pacific is about 1,000 years. But actually looking at the different types of tracers show that advection times of the fastest, if you want arrival type, can be of the order of like just 30, 40 years. So this is just if you want a bit of a review of some of the things that that we mentioned in this paper with like more recent work that I carried out actually with Sarah Perkey. And this was using different types of tracers. This is using chlorofluorocarbons and sulfur hexafluoride. This is like kind of passive tracers, if you want, in the ocean. It's what is shown here is the arrival time of one of these tracers globally and in the water, being carried by the waters that are in contact with the seafloor. So if you want, the plot here shows the kind of a proxy of the fastest like age of the water. So it's not the mean age, it's just the proxy of the arrival time, of the fastest arrival times of these waters. And focusing on, so basically younger arrival times means these waters have actually arrived. I mean, it didn't take a long time for these waters from the moment they are formed to reach that location. And vice versa, red points indicates that these waters have not been ventilated in the last few decades. And so this is what I was just saying, making the point that like actually waters have like from the Ross Sea where I've been formed have reached actually the North Pacific in just like 30, 40 years basically. And so the point of like that even the heat, for example, that they carry could have been affected of much shorter time scale than the ones reported in the paper. And then this is one of the other points that they touch very briefly, and this is part of, if you want, of ongoing work. So one of the key things that I mentioned in terms of the possible causes of the warming is that this warming could be a result both of changes in the properties of Antarctic bottom waters, in the sense that we are basically forming waters that are actually warmer, or it could just be a result of a shrinking in volume of these waters. And because of this analysis is done in a fixed volume, so in pressure space, if at a single location we have like a shrinking in volume, and so basically a contraction of the density levels and a contraction of the isotherms, this would show up as a warming. Even if it's like locally the water properties could have been cooling, for example. So this is then, of course, when we started like then discussing this, trying to separate basically these contributions. So contribution of water mass changes compared to what is called the heave, which is this mechanism, basically, if you want, of contraction of water masses, is important. This plot shows, this is like from a follow-up paper actually of Sarah and Greg Johnson in 2013, starting basically trying to dig into this analysis of separating different contributions. And what they show is basically like that the changes in different basins are could be caused by different mechanisms. And so that, for example, like while we think that the waters in the Ross formed in the Ross Gyre and along the Adelie coast, so in this part of Antarctica, are mostly caused by differences in water mass, in the sense that they have been like freshening a lot. Changes in the waters formed in the Weddell Gyre are actually caused mostly by heaving. So like what was before basically just plotted in general as a warming has actually underlined different mechanisms. And again, this is part of ongoing work. I have just a couple of slides on this because it's linked. I mean, this is actually what I've been working with Sarah and what I'm working kind of on now in terms of products. So sorry if it just jumps from the paper, but it's basically trying to use other tracers to dig into these different mechanisms. And very briefly, like basically we've been working, as I mentioned briefly before, with the chlorofluorocarbons or CFCs and sulfur hexafluoride or SF6. We know their atmospheric concentrations, which are shown here as a function of time. And we know that, so we know basically their surface boundary condition at the top of the ocean. And we have been measuring these tracers in the interior along different like repeated sections. And so we're basically using this information to constrain, if you want, the circulation from like basically to gain insights into when and where waters were last in contact with the atmosphere or were last in the mixed layer. And so how fast basically different ocean basins are being ventilated. And the connection between this work and the paper is that these tracers are entirely passive. And the analysis that we've been doing is in density space. So we don't have all the problems, you know, of like heat, of course, part of it can be redistributed as a passive tracer and part contributes to change the circulation. So we don't have, let's say, that issue with the CFCs. And at the same time, so that's like one of the main things. So these are entirely passive because again, also we don't have any source in the interior. And so the thing is that what we use basically these tracers to reconstruct a time mean circulation. And so we can then use it to look at the variabilities of different water masses or different, like for example, looking at the variability of the formation rates of different water masses. And this was an example actually in the Southern Ocean. So this is like a section like in front of the Ross Gyre. So basically like really in front of where you have the outflow of waters form near, in the Ross Gyre. And so, I mean, what is shown here, it's, if you want, it's a difference between like a reconstructed and observed concentration of these tracers. And what really tells us is that basically it tells us where the time mean circulation is not a good assumption. And when we basically, in this case, specifically tells us where the circulation was slower than the time mean circulation, which is everywhere you have these like red patterns. And so this is like a depth longitude section along this like section here. And the red contours indicate that basically the reconstructed concentration, again, assuming the time mean is higher than the actual concentration. And so this, it means that the time circulation was faster than the actual one. And so this is useful, again, connecting it with the paper, because this does not take, I mean, this analysis is done in density space. In this case, it's just remapped in dense space. So it does not have all the problem of the heaving that was in the previous analysis. This is basically just telling us the changes in formation rates rather than in the properties of the water masses. And so again, we are digging basically into how to use these tracers to better basically separate like contribution of the different processes to the warming that was like shown in this paper. And I think, and sorry, I don't really have a bigger conclusion in the sense that like that was the paper, and I think that's like basically a bit of a connection with that paper to what I'm currently doing now. So that's like one of the questions that we're trying to address. The other thing would be, sorry, okay, stop sharing and lost myself. The other thing is to look at also like patterns of other traces such as anthropogenic carbon. As like one of the other, like, of course, most climatically relevant. And that's it.
Thank you very much. Thank you. That's great. So before anybody else asks a question, what I immediately thought when I looked at this paper and thought about you, I mean, is there something detectably different really from their results to what we're seeing now? Is there actually a delta signal of climate change that's actually happening? Or is it too, I know there's extremely long life cycles and all the rest of it, but I just, that was the thing I was sort of curious about.
So that's actually partially what we're trying to do also with these other tracers, in the sense that to try to separate what could just be variability, like also even just decadal variability, which does emerge, for example, from the CFC's analysis, to what could be a longer term trends. It's always, I mean, they have large error bars, their estimates, because they're trying to include all the possible uncertainties linked to your question, like in the sense that you could just have a bit, variability in the westerlies, or variability like in the sea ice formations that could lead to changes in these fluxes. Long story is that's also why a lot of these trends are still not statistically significant. It's just mostly like a bit of a decadal variability, not really detected by these observations, because we don't have the time resolution needed. And we're trying to see if from other traces we can say something more basically about it.
Great, thanks. I kind of exploited my chairmanship there. Does anybody else have any questions?
Dominic?
Hi, thanks very much, Lara. I was just wondering a bit about the sort of the data sets that come out of these kind of observational missions, and whether you could say a bit about what models they're used in and how these data sets are used in other models. I just wanted to kind of contextualize it for myself in terms of other modeling efforts.
Yeah, I mean, this is just purely observational. And in terms of how, I mean, ECHO is a good example in which all of this data is usually directly assimilated. Which is, I mean, has been used by others, for example, like the transit and distribution in Green's function from ECHO has been used, for example, to reconstruct also the ocean heat content. And they kind of agree with the estimates like in the deep ocean with this. There is always an issue in terms of the model. I mean, one thing I've also been asked kind of many times, for example, why we don't use models to fill in the gaps between the observations, and that goes always back to the point you need to trust your model well enough. And a lot of the models, especially in the deep ocean, don't really do, in that sense, a great job. Access, from the, well, I guess Andy Hoggs and co-authors, a group like OMT6 is one of the models that we're trying to use, which seems to be doing a decent job. But even there, we have been doing a bit of validation tests with other traces, and their transport is not necessarily always the best in all the ocean basins. These observations are still, I mean, they go, I mean, this is, I mean, when we're lucky, it's decadal resolutions. I mean, when we're lucky, it's a bit higher. It's 5 to 10 years if you want, time span between the repetitions. I guess ECHO and SOSI, that's the Southern Ocean State Estimate, is another state estimate in the similar to ECHO if you want, but with the focus on the Southern Ocean, it might be actually, in a sense, a good product to go if the focus will be specifically on the Southern Ocean. So those are examples of state estimates that assimilate all of this data. There are other reanalyses also that could be used. And I know there are efforts to basically look at how these trends could be different in reanalysis, basically rather than just looking at the actual observations. And overall, most of the patterns agree in the sense of showing warming around the Southern Ocean, but a bit of some differences also emerge, and that is mostly also, just to pinpoint basically regions that definitely do need more observations. And for example, as the Deep Argo program hopefully spins up as a global program, those will be regions where to, for example, deploy more Deep Argo floats first. So how to prioritize that.
Great, thank you. Yeah, that answers my question really well. Thanks.
Anyone else? So then I'll ask one final question. You say you're about to go out on a cruise, right? Where you're similarly and looking at these different traces. I mean, how long does it take? Not saying when you write the paper. How long will it actually take for that data to be processed and used usefully to either update or modify the beliefs of what's going on in this? How long does the program take?
It doesn't take too long. I mean, if you think 6 months is not too long, because I mean, especially the cruise is done through Go Ship, which is this international airport, is quite strict in the sense of how, you know, how the data has to be shared, which is through like a CCHDO, is like a global, like international data set. Everybody basically can have access to all the cruise data. And so yeah, and within 6 months they have to be uploaded. And usually those are already being quality controlled. Which is great if you're like me, like for example, a person who likes to compile the data set just to download that. How these are like included then in other data sets like GloDAP. GloDAP basically takes all the available cruises. We also do another like controlling system, and that you just have it everything nicely if you want compiled in one product. They are also like trying to update that now at annual timescales. So every year there is a new GloDAP product, which is great, because before use was maybe every 5 years. So there is quite a lot of cruises in that sense been added. So yeah, it's quite fast. Sometimes there are parts of the data that are not always so easily shared. Like actually some of the CFCs have been not shared for like now some years, even if they should have been. So there are always a big caveats, but mostly it's like within 6 months.
Great. Okay. Well, then we can look forward to hearing the news in.
It's not that long if you think it takes 2 months for, like, I mean, I'm going to A16 North, as you mentioned, like I'm doing only half of it. It's a month. So just doing from the equator basically to Iceland, it takes about 2 months, because each cast is like around every 50 kilometers. And in areas of like high variability, that is even less. It's like every 30 kilometers. Right. So you stop quite frequently, and if it's deep, it takes a few hours, of course, to just reach the bottom and then come back up and do the analysis on board. Yeah. So 2 months for the cruise or 6 months to have the data is overall a good deal. Brilliant.
Okay.
So you'll be running the calculation like online, as it were, like as you go, you'll be calculating the mean.
Well, no, yeah, well, if everything goes well in that sense, yes. And I mean, if everything goes well, consider like the cruise started and like there was a wire circuiting during the first cast. The altimeter didn't work on the second cast, so they hit the bottom. So if you don't have any of those problems, yeah, you actually have automatically the profile right away. And if you have handy, as you do, like we do, like all the data from the past cruises, we can basically update this on the spot.
So, and do you, just to help my understanding, so you talked about the sort of the basin boundaries idea, where it's essentially almost like these kind of discrete packets that have different profiles for sort of various physical reasons. So as you traverse that space and you hit a basin boundary, are you then able to sort of take all those measurements from one particular region and say, okay, now we can compute the mean local heat flux for this region? Is it?
Yeah, that's how they did it here. Like it's like for each basin is like a length averaged, basically. Like if one section spans different like geographical basins, they just use the portion like within the basins, and then it's like a length average.
Yeah. So same method that you'll be using, or essentially.
Usually, to update this, yes. I mean, but what we're most mostly kind of worried is usually the linear fit, because in some cases it's not necessarily good fit. So again, they do calculate basically the error associated with that. They just kind of drop it if you want to some point, in the sense they don't really discuss in this paper. And I know Sarah has been looking at it, but not as in that sense as much. So we're just now especially because in some regions, for example, we saw the trends that have changed, like some regions were freshening, and now there was a reverse change. And some other regions would have been warming, and then again, there is a reverse change. So a linear fit in that sense is not necessarily the best, let's say, anymore. And so we're just trying to see if that's basically just going back to that part of analysis and how to change that.
And are you also measuring other variables like salinity as well at the time, or?
Oh yeah. I mean, it's a full spectrum in that sense. It's not, and it's not just let's say physical properties. It's also all biochemical, like particulates, organic matter, like the acid dissolved in organic carbon. There are CFCs and EFSA6. There are like different teams on board. Turbidity as well in many locations. So it's actually a host.
Yeah, a lot of stuff.
Yeah, and I was not in the sense too familiar with the rest, but that's why we have, I guess, different teams on board. Just basically two or three people specializing in just one type of observations.
Great.
Okay, I think that might be time to draw it to a close. Thank you very much, Lara, and thanks to everyone who came. And I think I actually recorded it, so that will be able to be circulated. Okay.
Thanks, Hannah.
Okay. Goodbye, everybody. Bye bye.
See you all soon. Thank you.